Chemtech laboratory tutorial. Today we'll be looking at nuclear chemistry. So, if we want to look at it, we said nuclear chemistry has to do with the study of radioactivity. It has to do with the study of radioactivity. And this radioactivity is a spontaneous reaction of unstable atoms. That is, atoms that are not stable, they tend to undergo radiations. They tend to undergo reactions that leads to emitting radiations. And these radiations include the alpha particles, beta particles, gamma, and we also have beta, which can be positive or negative. We also have electrons and neutrons. And these particles can be stopped depending on what the element will emit. So we now say that why do we need to study nuclear chemistry? During the time of Marie Curie, they were just in the experimental lab, and they discovered that the orano elements that they put under their cupboard were emitting rays. They wanted to be sure if this element is emitting rays. They have to put black body, and they noticed that some of the rays passes through the black body while some remains on the black body. So it is these rays that killed Marie and his husband Perry. So that is why we usually call them Marie Curie chemistry. So now they were able to measure the amount of rays that were given up. They were able to measure the amount of rays that were given out, and they were also able to measure the disintegrations of this unstable element, and at what point does this element becomes stable. So that takes us to what we call isotopes. We know that isotopes are elements that have the same general formula but different structural formula or different mass number. Now, for example, if we have carbon, we know that the mass number of carbon is 12, and the atomic number of carbon is what? 6. But they now discover that carbon itself can have a mass number of 14, and the atomic number is 6. So this becomes an isotope of this other carbon. But which of them is not radioactive? This becomes radioactive because it begins to emit rays. It's unstable because this is the only stable carbon that we know. But the isotopes of carbon becomes what? Unstable. Why? Because it emits what? Rays. So like I said today, that we are going to be doing some calculations on radiations. And what are these calculations? We are going to be looking at the binding energy. According to Albert Einstein, he said energy is directly proportional to the speed of what? Light. Where we now have E is equals to mc square. E is equals to mc square. So, sorry for that break. We needed to get our marker. E is equals to mc square. So this m is the mass of the electron. Now in chemistry, we talked about, in physics, when we say mass of the body. Do you understand? But in chemistry, we are looking at the mass of the products minus the mass of the reactant. That is, each of these atoms exhibits their mass. They exhibit their mass. So this mass becomes change in mass, which we call mass defect. Mass defect, and this mass defect means mass of the product minus mass of the reactant. Change in M will be equals to mass product minus mass reactant. And we are looking at mass of electron as to the mass that was the normal mass of one electron, which we know to be what, 1.6 times 10 raised to the power minus 32. So we are now looking at, if for example carbon is exhibiting mass, what is the atomic number of carbon? 6. That means we are now saying that the mass of this carbon depends on what? This atomic number. So we will take it gently, we will take it step by step. Now, looking at this, we will first understand the kind of nuclear reactions that occur before we can now calculate the energy of those nuclear reactions. If we have tritium, uranium is U234, and the atomic number of uranium is 92. We say this uranium will disintegrate because uranium is what? Unstable. Any element that is above 80, any atoms or element that is above 80 is assumed to be what? Unstable. So those elements, that is, we are talking about the atomic number. Now, if those elements are above 90, we say is what? Unstable. And if they are unstable, it means radiations can occur. It means spontaneous reactions can what? Occur. And this spontaneous reaction can keep on emitting rays until we get to a stable what? Element. So if we have uranium, for example, it means we can say uranium can give us neutron to be 2. The atomic number of proton is 90. So if we have 90, what kind of rays do we now have that are giving us? If the mass number is 234, it means we will say 90, what we add to 90 is what? 2. Is what? 2. So that means it has to emit 2 what? Positron. 2 positron. Positron is something that is a positive aspect of what? Of a beta particle. You know, beta particle is 0, E minus 1. Then the positron of the beta becomes +1. It increases the atomic number, while beta decreases the atomic number. Sorry for the break. So welcome back. So we have types of radiations. What are these types of radiation? We said the types of radiation include alpha radiations, beta radiation, gamma radiations. So those are the 3 major radiations that we have. Although there are others like the X-ray, we have X-ray radiation. But what are the difference in this radiation? They, for the alpha, it emits alpha particle. And what is alpha particle? Alpha particle, they are particles that we usually call them helium. We call them what? Helium. They have mass number of 4 and atomic number of 2. So they are represented with the symbol alpha. So it can be written as this or this. That is for alpha particles. So what do? They either, what they do is to increase the mass number and also increase the atomic number of what? Any particle that what? Exhibits alpha particle. More also, these alpha particles can be stopped by what? A piece of paper. It can be stopped by a piece of paper or a foil paper. Either of those two can stop what? Alpha particles. It has a high penetrating power, but when you are comparing it to that of gamma, the penetrating power is less than that of gamma. But when you are comparing it to that of beta, is higher to that of what? Beta. So the penetrating power means the rate at which the rays travel through a particular material. That is what? Penetrating power. Same with beta. Beta is represented as it has a 0 mass number and decreases the atomic number of element. That is why it's called zero. Is represented as 0 and -1. The opposite of beta is called a positron. It's called what? A positron. And that positron is that the atomic number increases. It increases the atomic number of the element. That is +1, while that of beta is -1. It has no max number. It has no max number. And also, it is negatively charged and it can be stopped by a piece of paper. It can be stopped by a piece of paper. But that of gamma, gamma has no max number, neither does it have an atomic number. So it does not even increase or decrease the elements that exhibit a gamma particle. Neither does it increase the atomic number of the element that exhibit gamma particle, but it has a strong penetrating power. The penetrating power of gamma is higher than beta and what? Alpha. It's higher than beta and alpha. And more also, this gamma particle can only be stopped by a lead block. That is, you put a lead block in between the rays and it stops the ray, it does not pass through the red block. So that is the difference between these three particles. Now we are going to take some reactions, some nuclear reactions of this particle. So we'll go on break, take the reactions. So I'm going to go through some questions on the comment section and see what you are talking about. Let's take some comments before we move further. Okay, is faint. Okay, we have improved by bringing a sharp marker. Thank you. Thank you for that. Then how do they know they were emitting rays? That is Grace Smith. He said, how do they know that they emit rays? We only like I told you earlier, that any atom that is above 80 in the atomic number, any atom that is above 80 in the atomic number, that atom will emit rays. Any atom that is above 80, because 80 is lead, and lead seems to be the stable element. So any atom above 80 will emit what? Rays. And why do they emit rays? They emit rays because they are unstable. They are what? Unstable. They exhibit, they use, when energy are bombarded to the central atom, and the central atom, we know that is called what? Nucleus. And we said the particles of nucleus are proton and neutron. So the neutron there tends to what? Be unstable. And since it's unstable, it will emit rays. Now the next question, before we take reactions, we look at the next question. Said the camera is blurred. Sorry, we will improve on that. Success is asking, ma, for the beta, you said what? Okay, for the beta, we said the beta particles emit rays, and the rays it emits is represented as 0 as max number, no max number, then -1 as the atomic number. It's on the board there. That is beta rays. Beta what? Rays. So any particle that is unstable can emit a beta particle, and that particle is represented as no max number, and the atomic number is -1. Okay, the next says, how can we stop beta particle? I said we can stop beta particle with a sheet of paper. We can stop beta particle with a sheet of paper. Can beta particles, now I'm trying to get to the next person's question, by Rixin, Dovi Rixin. Alpha particle. He said, ma, please, I thought beta particles are stopped by aluminium foil. You said piece of paper. Yes, it is alpha particles that can be stopped with what? Aluminium foil, and beta particle with what? A piece of paper, a thin paper. Okay, say, ma, you are too fast. Okay, we'll take it down little by little. Thank you. You know, this is the first time we are going on live, so with time we will get used to, I will get used to taking it slow. Okay, thank you. So I think that is all for all the questions. That is all for the questions. Now the next one is to know the pattern of stability. The pattern of stability. How do you know that an atom or an element is stable? How do you know that atom or element is stable? So how do we know? Like I said any element that is above 80, it is what? Stable. Any element above 80 in the atomic number is stable. But meanwhile, we have what they call nuclei above the belt of stability, and we also have nuclei below the belt of stability. Belt of stability meaning that if the atomic number is less than 80, will it be stable? Or if it is more than 80, will it be stable? So that gives us to what we call isotope. So I'm taking it gently now. So what is isotope? We said isotopes are elements that has a general formula, but or a general atomic number, but different mass number. So if you are having an element with a different mass number, then you will know that the number of neutron will change. If, for example, we have carbon 12, carbon 13, carbon 14. Carbon 12 means is the atomic the max number, the carbon has a max number of 12. Carbon 13 is the the carbon has a max number of 13. Carbon 14 is the carbon has a max number of 14. But now we now represent this to be, it is represented as what? Look at it. We are going to clean up this and look at stability. So it is represented as C12, C13, C14. We are just using carbon for instance to explain why we said depth of stability can be low or can be high, or it moves towards stability. Now if we have 6 here, we have 6 here, 6 here, it means these three are isotopes of each other. They are what? Isotopes of each other. Why are they isotopes of each other? It has a atomic number of 6, but the mass numbers are what? Different. So within this, what will be the number of neutron? Number of neutron will be equals to, for this particular carbon, 12 minus 6 will give us 6. That is number of neutron. But for this particular one, 13 minus 6 will give us what? 7. That is the number of neutron for this carbon. Then 14 minus 6 will give us what? 8. That is what? The number of neutron. Number of neutron. Neutron for this carbon. So you see that the number of neutrons are different. Now how do we know that these carbons of different mass number are stable or are not stable? That is when we talk about the neutron proton ratio. Neutron proton ratio. Neutron proton ratio. It is the neutron proton ratio that tells us if an element is stable or not. Now if the neutron proton ratio is equal to 1, it means what? It is stable. But if it is greater than 1, it means it is not what? Stable. It means it is not what? Stable. So let's do the mathematics. Proton neutron for this is 6 all over 6. That is for this particular isotope, C12. 6 over 6 is equal to 1. So we call this a stable element. But if you come to this other one, 7 over 6, somebody should type 7 over 6 will give us 1 point something, either 1.2. Will give us 1 point. That is neutron to proton ratio. So 1.6 into this will give us 1, balancing 1. 6 add 6 to it, 1.20. So you see that it is greater than 1. So this is not what? This will try to move towards the belt of stability because it is not what? Stable. But if you look at 8 divided by 6, 8 divided by 6, which is for this carbon 14, 8 divided by 6 is what? 1.4 or so. 1.3. We have it as 1.4. 1.4. So you see it is higher. I think it's 1.31. 1.31. So you see that it's what? Higher. Now it means this bond is moving towards stability. So we cannot classify this carbon 13 or carbon 12 to be what? Stable. Why? Because of the proton to neutron ratio, which determine what? Stability of an element. So this one we tend to move towards the belt of what? Stability, because the belt of stability is what? 1. And we said the atomic number based on stability must be below 80. Any atomic number below 80, that is less than 80, is what? Classified as stable. Now that based on what? neutron to proton what ratio. So if the neutron to proton ratio is greater than 1, it means that compound, that element is not stable. So it will move towards the belt of stability. It will move towards the belt of stability. So that is it. That is how to classify stability. So that is how to know the stability. So what are the factors that affect this stability? What factors affect stability? Radiation, half-life, number one. Half-life affect what? Stability. But before we go into factors that affect stability, we will look at the reactions, the nuclear reactions. The nuclear reactions. So let's look at the reactions together. Under each of these decay, we are looking at it under what? Okay, somebody is confirming for me that alpha particle is stopped by a sheet of paper and beta particle is stopped by foil paper. Okay, thank you. Alpha particle is stopped by uh, uh, a sheet of paper. Alpha particle is stopped by a sheet of paper and beta particles are stopped by aluminium foil. So before we go further, we will look at the reactions based on the types of radioactive decay. Based on the type of radioactive decay. So let's look at it one after the other. So starting from the alpha particle or alpha radiation, can be alpha particle or alpha radiation. Let's use uranium. If uranium, we know uranium to be what? 92. Let's assume is 3, the max number. We are not assuming because we said radiations we consider their isotopes, because we believe that if the proton to neutron is greater than 1, it is not what? Stable. So if you have 238 as the mass number of this uranium, which is 92, this uranium tends to undergo disintegration. It tends to undergo disintegration. Disintegration means spontaneous reaction to different, for it to that enables it to undergo what? We now have 2 and 90. This is 90, the max number. What atomic number bears 90? Thorium. And this means what? 4/2 helium. This is how to balance nuclear reaction. Nuclear reaction is quite different from chemical reactions. In chemical reactions, we look at the number of moles, the stoichiometry of the reaction to balance what? The reaction. But in nuclear reactions, we look at the number of neutron to what? Proton. Meaning 238 is the max number, 92 is the atomic number. So if you look at this place, we have 2, 3, 4 and we have 90. How do you balance? It means we will need to add what? An alpha particle, which is 90 plus 2 to give us 92. Then 2, 3, 4 plus 4 will give us 2, 3, 8. Will give us 2, 3, 8. So this shows that the reaction is what? Balance. So this is how to balance reaction. You can have radium. Radium is the atomic number for radium. If you check the atomic number for radium, I think it's around 84 or so. It's around 84. radium. So someone should check the atomic number for radium for me. Check the atomic number for radium for me. You can have it to be, I'm trying to remember that, 84. Then okay, the radium atomic number is 88. And you can have it as 226. That will be the max number. The max number can be 226. The max number can be 224 if it exhibits in what? In isotopic nature. So 888. So if we take it to 888, that means if this element is bombarded with energy, it means we will have Renault, and that will give us what? 86. 86 plus what? 222. That will be the max number. So how do you balance it? We balance it with what? An alpha particle. And this is how it goes. 86 plus 2 gives us 88. 222 plus 4 gives us 226. So you now balance this one for me. If I have thorium to be 90, I have 2, 3, 4. What will be X if it exhibits alpha particle? What will be X if it exhibits alpha particle? So do that for me. I'm going to the comment section to take some questions now while you are working on this for me. Thank you. Okay, I'm trying to go through the message, but I'm noticing that I cannot go through it through my phone. So let me go through someone else's phone. Another moderator just handled this.
No.
Okay, I think we'll go on break. Let me see, because I can't go through the message now through my phone. They are telling me another person has
taking over. Let me know the person, please. And I'll start all over again from the nuclear chemistry. Let's take a break and see what is going on, please.